In the previous video, I wrote a first definition of Taylor polynomials. In this video, I will translate it into a second equivalent definition which is more useful for computations. Let's recall what we know. The nth Taylor polynomial for the function f at a real number a is a polynomial which is an approximation for f near a of order n. This means that as x approaches a, the difference between the function and the polynomial approaches 0 faster than x minus a to the n. In the previous video, I explained why this limit being 0 means that the polynomial is a good approximation for the function. And I also requested that the degree be at most n. As I explained, this definition encapsulates exactly what the important property of Taylor polynomials is, why we care about them, why they are useful. However, it is quite abstract and it is not very useful for computations. I cannot easily use it to compute the Taylor polynomials of a function. Based on this property alone, I don't even know when these polynomials exist. My goal is to translate this property into a second equivalent property that is easier to use, particularly for computations. Before doing that, I want to introduce some new notation. A function is called C0 when it is continuous. Sometimes it is also called type C0 or class C0. It is called C1 when the derivative exists and is continuous. It is called C2 when the first and second derivatives exist and are continuous, and so on. It is called Cn when the first n derivatives all exist and are continuous. And it is called C infinity when all the derivatives exist and are continuous. I could use all these concepts at a point or on an interval. Why do I introduce these names? We are going to encounter quite a few results that require different amounts of derivatives to exist and be continuous. It is nice to have a name for these concepts. That's all. It will make the statement of theorems a bit shorter. Okay, now that I have this notation, let's move on. For now, let's assume that f and g are C infinity. They have all their derivatives. I want to try and rewrite this condition, that the limit as x approaches a of their difference over x minus a to the n be 0. I want to rewrite this condition into something simpler involving the derivatives of f and g. As I said, for now I will just assume that f and g have all their derivatives if needed. Once I finish my exploration, I will check back and see which assumptions I actually used. Let us call this limit L. I'll admit that this notation is a bit problematic because this limit may not exist, but for simplicity, I'll refer to this expression as L whether the limit exists or not. I have the limit of a quotient. The limit of the denominator is 0. Since f and g are continuous, the limit of the numerator is f of a minus g of a. If f of a minus g of a is not 0, then I will have a non-zero number divided by 0. The limit L will be plus or minus infinity. And possibly the limit on the left and the limit on the right will be different. But in any case, L will not be 0. So let's discard that case. Let's assume that f of a equals g of a. In that case, I get 0 over 0, an indeterminate form, and I can try to use L'Hopital's rule. After using L'Hopital's rule, L becomes the limit as x approaches a of f prime of x minus g prime of x over n times x minus a to the n minus 1. I put an asterisk over the equal sign because this is only if the use of L'Hopital's rule ends up being justified, if this limit ends up being a number or infinity or minus infinity. Otherwise, the use of L'Hopital's rule was not legal, I could not do this, and I know nothing about the original limit. Fortunately, that won't happen, as I will explain later. Now, we are exactly in the same situation as before. Assuming n is large, the denominator has limit 0. The numerator has limit f prime of a minus g prime of a, because f prime and g prime are continuous. If f prime of a minus g prime of a is not 0, I get a non-zero number over 0. The limit is plus or minus infinity, possibly different on the left and on the right. The use of L'Hopital's rule was legal and L is not 0. So let's discard that case as well, and assume f prime of a equals g prime of a. Then I have an indeterminate form of type 0 over 0 again. I use L'Hopital's rule again. And I keep going. After using L'Hopital's rule n times, I get that L equals the limit as x approaches a of the difference of the nth derivatives on the top over n factorial on the bottom. And since the derivatives are continuous, I simply evaluate at a. Great, I think I have found the conditions for the limit L to be 0. I needed all the previous derivatives of f and g to agree at A. This is how I kept getting indeterminate forms of type 0 over 0 and I could use L'Hopital's rule. And I also need the nth derivatives to agree at A, so that the limit is finally 0. To be clear, this is an if and only if. These are necessary and sufficient conditions. I have shown that if I have all these conditions, then all the uses of L'Hopital's rule were justified and the limit L is 0. On the other hand, what happens if any of these conditions fails? If the last condition fails, then the limit L is a non-zero number. If any of the previous conditions failed, then at an earlier stage one of the limits could have been plus or minus infinity, possibly different on the left and on the right, and therefore L wasn't 0. Finally, notice that in this whole process, I have used that f and g were Cn. I did not need C infinity after all, but I did need Cn. I have proven a theorem that is worth stating. The theorem says, let f and g be Cn functions at a point A, then the following two conditions are equivalent. 1. As x approaches A, the difference between f and g approaches 0 faster than x minus a to the n. And 2. The first few derivatives of f and g have the same value at A. So, g is a good approximation for f near A, if and only if g and f have the same first few derivatives at A. How good an approximation? That depends on how many derivatives they agree on. I need to acknowledge that the proof I have written could be made more formal. I could use induction instead of saying I repeat the process n times, but I am just going to leave it at that. In any case, this is exactly what I was looking for. I can now take the definition of Taylor polynomial, which I had written using condition 1, and rewrite it using condition 2 instead. Here we go. Let A be a real number, n a natural number, and f a Cn function at A. The nth Taylor polynomial for f at A is a polynomial, which I will call p sub n, such that the polynomial and the function have the same value at A, and so do their first derivative, their second derivatives, and so on, all the way to the nth derivatives. And in addition, the polynomial has degree at most n. As I said at the beginning, this definition is simpler than the original one. I am just specifying the value of the polynomial and its first few derivatives at A. For the purpose of constructing these polynomials, for the purpose of computations, this is more useful than the original definition. But I think we should always keep in mind the original definition as well, the one in terms of the limit. It tells us why Taylor polynomials make good approximations. Notice that this is not a completely new idea. We have encountered it before. What could be the first Taylor polynomial according to this definition? It should be a polynomial with degree at most 1, whose value at A is f of A, and whose derivative at A is f prime of A. That is how we define the tangent line. Great, this definition makes sense. In the next video, I will take this one step further and make it even more concrete by providing an explicit formula to construct these polynomials. Then, from there, I will be able to compute examples. Stay tuned.